In this video module, we'll be looking at generating random variates. And this is a lecture or a module that I like to call quick and dirty random variate generation, because we're going to look, just hit the highlights and look at a couple of very simple methods for generating random variates that you can use in simulation models. Note that this is a very robust topic, random variate generation, and there's lots and lots of material if you're interested in studying the area in more depth. And so I like to start out with this Dilbert cartoon, one of my very favorite Dilbert cartoons, by the way, where you have Dilbert taking a tour of the accounting department, looking at their random number generator, which is of course generating numbers 999, 999. Dilbert then of course questions the randomness here, and Monster says, well, that's the problem with randomness, you can never be sure. And in fact, that's true. It's very difficult to tell if numbers truly are random. In fact, from a computational standpoint, it's impossible to generate truly random numbers with a computer. You can't do it. There has to be an underlying algorithm to generate the random numbers, and that underlying algorithm prevents randomness. So if you want truly random numbers, you need to use some type of mechanical method, like drawing ping pong balls or casting die or something like that. And that's one of the reasons when you watch lottery drawings on TV, they always use a mechanical method for drawing the random numbers. However, while it is impossible to generate truly random numbers with a computer, we can use computer algorithms to generate what are called pseudo-random numbers. And these are essentially numbers that are close enough for our purposes. So for our simulation models, the pseudo-random numbers that are generated by our computer algorithms are close enough to actual random numbers that we can use them in our models. And so what we're after is generating observations from random, or generating observations of random variables from various distributions. And you can see that I have drawn here our uniform distribution, and so we know the uniform distribution looks sort of like that. And we have a normal distribution here, which has its central tendency, symmetry, and so on. We have an exponential distribution, a triangular distribution, which we'll talk more about later, and finally a log normal distribution. And so in this module, what we will look at is how we can generate observations of these random variables that follow these distributions. So our quick and dirty method generally involves a two-step process of generating what are called or what we're going to call U01s, or uniformly distributed random variates on the interval 0 to 1, and then transform these UIs into observations from the desired distribution. So let's look at this U01 in a little bit more detail. So if we look at the density function, we have f of x, and it ranges from 0 to 1 and 0 to 1. And so this is what the density function looks like. That's 1. And then the CDF, x fx, again 0 to 1, always for a CDF, and the interval here, and so it goes from 0 to 1, and then it stays at 1. And so we can see that the basic property of the U01 is that all of the values between 0 and 1 are equally likely. And so for our quick and dirty method, we're going to assume that we have a built-in method to generate these U01s. So if you happen to be using Excel, you can use the rand function, and the rand function will return a U01. And most programming languages also provide built-in functions to generate these U01s. And so the basic idea is that I'm going to sample these guys, these U01s, and then transform those into observations from the desired distribution. So the first method that we're going to look at is called an inverse transform method. And the basic idea here, let's see if I can, whoops, I want to change colors. Changing colors, black. The general idea is that we're going to use the CDF of the target distribution. And so let's say I have f of x, that's an x, and it goes from 0 to 1 to CDF. And let's say our distribution looks something like this. Doesn't really matter at this point what the distribution is, but let's say it looks like that. And so the basic idea on when using an inverse transform method, let me change ink colors one more time, is that I'm going to sample a value here that we're going to call UI, and then we're going to invert the CDF to get gamma UI, which is what we're after. So gamma UI is an observation of the desired random variable. So it's from the distribution that's defined by f of x. And so, as we said before, it's a two-step process to sample these random variables. We're going to sample a U01. And so you can see a U01 is going to be uniformly distributed along the 0-1 space. And so then when we invert the CDF and we solve for gamma, we're going to get random observations, or actually pseudo-random observations from the desired distribution. The first distribution we're going to look at, well, I don't know why this slide's repeated. There we go. The first distribution we're going to look at is the general uniform distribution. So it's no longer U01, but it's U ranging from A to B. And so here we have the density function. Oops, that's not what I wanted to do. And we also can have the CDF. So we have x, f of x, and in this case, here's A, and here's B, 0 to 1, and so it is 0 till we get to A, and then it goes linearly till we get to B, the value of 1, and as so. And so the basic idea for an inverse transform, as I said before, is we're going to sample a value along here, and then we're going to invert to get our gamma value. And so we can do that by using this component of the CDF. So I'm just going to repeat that and say f of x is equal to x minus a over b minus a. And I'm simply going to replace f of x with u, our u right here, and x with gamma, minus a over b minus a. And then I'm going to solve for gamma. So I'm going to get u times b minus a equal to gamma minus a, where gamma is equal to a plus u times b minus a. So I can sample my u and then solve this expression to get observations of gamma, which will be uniformly distributed on the interval AB. So let's have a look at that in Excel. So I can go to my Excel workbook, and let's say I want to generate uniform between, say, 10 and 100. And so we can see that our b minus a is 90. And so if I say my u here, and let's just say the corresponding gamma here, of course, as I mentioned, we can get using Excel just by using the rand function. And so as I generate, or as I type the rand function, it generates an observation. And in Excel, the recalculate button will sample a new value. And so now I can simply solve for gamma by saying my gamma is going to be a plus u times b minus a, right like that. And so now we have an observation of our random variate that's uniformly distributed between 10 and 100. And I can generate additional observations by editing the formula I have here and making my references to a and b minus a absolute references rather than relative references, and just leaving my b6 reference as relative. And so now I can just simply copy these two cells, and let's copy down to, say, 25. And so now what I have is 25 minus 6, so 19 observations of a uniformly distributed random variable on the range 10 to 100. So going back to our Dilbert cartoon, when we look at these observations, naturally we have the question of, well, how do we know this is right? And so I'm going to look at a different worksheet that's on the website that just expands that sampling. And so in this case I have my A and B, and here are my u's, and I generate two different observations, a continuous observation, which is what we just did. You can see the same formula here, which is a plus the u times the range space, which is b minus a. Same thing that we did before. And in this case, I'm generating a lot more observations. So I'm actually generating 5,000 observations. Go back to the home here, control home. And what I did over to the right here is that I computed some descriptive statistics from my sample. And then we drew histogram. We used the frequency function coupled with drawing bar charts to show that the histogram, show the estimate of the density function for our distribution. And so what we expect to see, again, is equally likely observations between 500 and 3,500. And so while we don't have proof, this looks pretty strong that we have the appropriate uniform distribution on the range that we want. And of course I can change these values, so I can make this one say 200, and let's make this one, well, I guess I can't do that because I haven't updated the, I would have to update the frequency, so I'm not going to do that. But what I do want to do is look at recalculating. So in Excel, we can recalculate either by choosing recalculate or hitting F9. I can't hit F9 on my computer because it interferes with the recording software. So I'm just going to recalculate. And what I'm doing every time I recalculate is I observe the values for my descriptive statistics here and just watch my histogram and make sure that it looks to be uniformly distributed on the desired range. And because this is the quick and dirty random variate generation module, that's all of the validation that we're going to do. We're just going to look at the histogram and look at the descriptive statistics, go through several different samples, and just make sure it looks okay. There are many statistical tests we could do to make ourselves more confident that we're actually sampling what we think we are, but that's a topic for another module. The next distribution that we'd like to look at is the exponential distribution. So we can see here the density function, and of course the CDF looks something like this. We have our 1 here, and something looks like that. And so our general process is the exact same. We're going to sample a U, and then we're going to invert the CDF to solve for gamma. And so we can easily do that using the same method that we did with the uniform distribution, as we'll replace the fx with a u, and this will be 1 minus e to the minus lambda gamma u. And then we can simply solve this for gamma of u, and we end up with gamma of u is minus 1 over lambda times the natural log of 1 minus u. And so we can use this inversion of the CDF the same way that we did with the uniform distribution. So if we go back to our spreadsheet, let me find it here, and you can see we have the exponential distribution, or sample of the exponential distribution here, where we have the mean value and lambda. Recall for an exponential distribution, lambda is the rate, and 1 over lambda, sometimes referred to as beta, is the actual mean of the distribution. And so we have our u values using rand, and then we have our expression minus 1 over lambda times the natural log of 1 minus u. Of course, in this case, you can see that instead of 1 minus u, we're using just the u value. And so let me go back a second and talk about that for a second. So this is the expression that we developed. Since u is uniformly distributed, let's see, since u is uniform 0, 1, then 1 minus u is also uniform 0, 1. And so that is why we were able to use the u directly rather than the 1 minus u. So the actual expression that we used in the Excel spreadsheet is gamma of u is equal to minus 1 over lambda times the natural log of u. Keep in mind that this only works because we're looking for a random value. In another context, if we were looking for a particular quantile, For example, if we were looking for the 0.25 quantile, then we couldn't replace the 1 minus 0.25 with 0.25. We would still have to use the original value. And we'll get to that a little bit later on. So again, with using the same method that we did for the uniform distribution, our validation method is basically to look at the descriptive statistics, the average and the standard deviation. We know with an exponential distribution, the mean and the standard deviation are equal, and then we also look at the general shape of the distribution that clearly has an exponential look. And so we can go and do another recalculation and sort of watch the different samples and watch how the descriptive statistics and the histogram change, and based on just our casual observation, it appears that this is in fact a good sample, a good method for sampling from the exponential distribution. So to summarize, in the inverse transform method, what we did was we took the CDF and then we inverted the CDF so that we sampled along the range space, which is between 0 and 1, because it's a probability, it's always between 0 and 1. We picked a random spot along the axis, and then through the inversion expression, we then solved for the observation that we wanted. And this method, this inversion method, works with any distribution that's mathematically invertible. In the next video, we will look at a couple of additional distributions where we can't directly invert the CDF, and so we have to use a different method to sample from those distributions.